everyone, I hope you are all doing well. Welcome back to Algorithm Simplified, and today we're going over the binary search solution for number 410 split array largest sum. It gives you an array of integers and also m, indicating the number of subarrays it would like you to split this integer array into. Your goal is to split nums into m subarrays such that the maximum of each of the sums of ints in the subarrays is minimized. So for example, one way we could split this array right here is, say, like so, into m equals 3 subarrays. While here for this subarray we have 6, which is a really small number, and here it's only 11. For this first subarray, we would have an ultimate total of 26. For this split in particular, we would have a value of 26. But that's not the best way we can split it. In fact, one of the best ways we can split this example right here is actually as follows. We could split into 7 and 12, 2, 5, and 6, and 8 and 3 to give us 19, 13, and 11 as the sums accordingly. Ultimately, 19 being the maximum, we return 19, the best, minimized of the biggest sum possible for the split array. The key to the binary search approach to this question is to not use binary search as a means of searching through every single individual value in our nums, like you usually do with binary search. But what you do instead is you use the lower and upper bounds of what the return value could be to do a binary search. Let's walk through the example. So what would the low and high bounds be for the possible return value, despite of what m could be? The lowest possible value we could return is the maximum of the nums, because each subarray has to have at least one value in it. And the best case scenario, assuming m is big enough, is that we would have nums be split off into n subarrays like so. And in this case, the maximum of those values would be the max of the nums. The upper bound, the worst case, is if we only have one m. We can only split this array into one possible subarray. Then in that case, our upper bound would be the sum of nums, in which case low would be equal to 12 and high would be equal to 43. While low is less than high, we're going to do binary search. In our first iteration, our mid value would be the middle point between 12 and 43 floored, which would be 27. Now taking this mid right here, we're going to see if our nums is splittable into m subarrays, so 3 subarrays, at the sum of each one being less than or equal to the mid's bounds. So if we start at 7, that's initially a sum of 7, that's less than 27, so we continue. Moving forward, 7 plus 12 gives us 19, that's still less than 27, we continue. Here we get 21, 26, and we stop. Because if we add the 6 afterwards right here, we're going to get something greater than 27. So this is one subarray. Moving forward, this has a sum of 6, plus the 8 gives us 14, plus the 3 gives us 17, which is less than 27, meaning we're able to split this off into 2 subarrays of sums less than or equal to 27, and that is indeed less than or equal to our m of 3, meaning that our midpoint is actually too high for the value we should return at the end. So we update our high to be equal to mid, like so. Now let's look again. Is low still less than high? Well, yes, it is. So let's continue. On our second iteration, our midpoint's going to be the middle between 27 and 12, which would be 18. Now let's check if nums is splittable into 3 subarrays, where each of the subarray sum is less than or equal to 18. Starting off, we have 7 here, but we can't continue to 12 because otherwise we get 19, which is greater than 18. So this is one subarray on its own. Starting again at 12, we have a sum of 12, then 14, and we can't continue, otherwise we hit 19, and that's too large. That's a second subarray. We start at 5, move on to 6, 11, and we can't move on, otherwise we hit 19. So that's its own subarray. We start at 8, gives us 8, move forward, we get 11. Since we have 4 subarrays split, and 4 is indeed not less than or equal to 3, then what we do is we change the low to mid plus 1, meaning this mid value is too low for the value we should return. On our third iteration, the midpoint between our low and our high would be 23. Let's see if we can split our nums array into 3 subarrays with each sum being less than or equal to 23. We start at 7, move forward, gives us a sum of 19, move forward again, gives us 21. We can't continue anymore, so that's 1 subarray. We start again at 5, move forward, gives us 11, then we move forward again, gives us 19, move forward again, gives us 22. Since we can split this into 2 subarrays, which is less than or equal to 3, this means that yes, indeed, we do need to change our high to be equal to our mid, meaning that this mid value right here is too large for our return value. Since low is still less than high, let's continue. For our fourth iteration, our midpoint is going to be 21. Similar to before, we do 7, here we have 19, here we have 21, and that's 1 subarray. Move forward, 5, 11, 19, we can't move forward because that's 22 and that's too large. So that's a new subarray. 3 by itself finishes it off. That's 3 subarrays, and that is indeed splittable into 3. We need to update our high to be equal to our mid. On our 5th iteration, our midpoint would be 20. We repeat the process. Start at 7, move to 12, gives us 19. We stop right there to form its own subarray. Start at 2, move on to 5, giving us 7 sum. 13, can't move forward, so that's a new subarray. Start at 8, move on to 3, gives us 11. And since 3 is indeed splittable into 3, we change the high into the mid. For our 6th iteration, our midpoint would be the lower bound, meaning between 19 and 20, our midpoint would be 19. Is our nums array splittable into 3 subarrays at sum is less than or equal to 19? Let's find out. Start here, go to 7, 12, 19, that's 1 subarray. 2, go to 5, gives us 7, go here, gives us 13, can't continue, that's 1 subarray. Here, we start with 8, move forward, gives us 11, that's 3 subarrays. 3 less than or equal to 3, meaning that yes, we can indeed split our subarray so that the max sum is 19. So we update our high value to be equal to our mid. And since our low value is no longer less than high, since it's equal to high, we return, finally, our high value, 19. This matches what we have discovered previously about the best solution. In terms of big O analysis, binary search itself is performed on the high upper bound of the sum of nums. So that would be log of s, where s is the sum of nums. For every single iteration of the binary search, we need to go through the nums array to check if it is splittable into m subarrays. So that has to be times by n, where n is the length of nums, giving us a total of O of n times log s. In terms of memory, Since we only have constant pointers, our memory is O of 1. Before I show you the coding solution in Python, if you've enjoyed this video so far and you will like my explanations and detailed walkthroughs, please do consider subscribing, liking, and commenting on the video, as it tells YouTube that you like my content and support my content. That would mean a lot. Let's get into the coding solution. So first, we initialize the low and high for our binary search, being the max of our nums and also the sum of our nums accordingly. While our low is less than our high, we perform binary search. The middle is equal to the low plus the high minus low, floor divided by 2. I write it this way instead of writing it like low plus high, floor divided by 2, because in some languages that can cause overflow. Next, we need to check if our nums array is splittable into m or less subarrays with sums less than or equal to mid. So we initialize 2 variables, one being the sum so far and one being the total subarrays. Total subarrays we initialize to 1, because as soon as you start, you have to create a subarray. We iterate through nums. For num, in nums, there's 2 possibilities. If this num plus our sum so far is going to be less than or equal to mid, then we just add it to our sum so far. The other case is that we cannot add this current num to our sum. We have to create a new subarray. So our total subarrays will be updated to add 1 more, but our sum so far will be changed to num because we are starting a new subarray with num. At the end, we check if our total subarrays is less than or equal to m. If our total subarrays is less than or equal to m, meaning our mid value is too high for what we would return in our optimal solution, we update our high to be our mid. Otherwise, if our mid value is too small, we need to update our low to be equal to mid plus 1. At the very end of our binary search, we return the high value.